actually work inside the fire agencies and the land management agencies. And in Australia, we're a national agency, it's the Bureau of Meteorology, we're a Commonwealth agency, but all of the fire and the land management agencies are state-based. So it makes it really interesting from a jurisdictional perspective that we're a national agency, but we're working with all these state-based agencies. So that was me during Black Summer, briefing the Premier and the RFS Commissioner in Sydney, working alongside Simon Heemstra, who was our fire behaviour analyst. So we've got a really collaborative relationship with the fire agencies. I think it's quite different to what happens in Europe. We also do a lot of fire weather research in satellite, radar, as Adrian has said, pyro-CB prediction, some of my colleagues have been working a lot on that, ember transport, three-dimensional plume processes, and the main work that I've been doing, which is case studies with access fire. And we've also been doing a lot of work in soil and fuel moisture and in hydrological cycles, and really looking at the fuel availability in the landscape and how much is likely to burn. So happy to talk about that in the next few days as well. All right, so we do case studies. We use a coupled fire atmosphere model to do it. And why do we do this and what are we looking for in the modelling framework? So a lot of this goes back probably back to 2003 Canberra and even before, where there was observed fire behaviour that simply didn't reconcile with what people were expecting, and it didn't reconcile with the surface weather input. So if you look at your surface conditions of temperature, dew point and wind speed, it just simply didn't explain the fire behaviour that was being observed. And coupled fire atmosphere models are a tool for understanding the fire and atmosphere interactions, and consequently that improves our fire predictions because we can see processes in the coupled fire atmosphere model that really make sense of some of the situations that we didn't understand. As everyone probably knows, the impacts of climate change are really manifesting in increased intensity and frequency of synoptic and mesoscale weather events, and we're seeing more destructive fires. Why do we do case studies? As an operational agency, case studies are a really effective learning tool, particularly when you're talking to practitioners who have lived through an event. That context of lived experience is really valuable for learning and then applying that knowledge to the next event. We've got a really multidisciplinary approach to the data collection and analysis, and I'll show a whole range of data today, which then gives you a deeper context for learning. So you're looking at all the different things that were happening in the environment. When we're doing simulations, we really want to have a reasonable match for observations. It gives us the opportunity to test higher resolution simulations than what we can run in real time. And we want to look at various physical processes. So we want to have similar model outputs to what we're looking at in operations so that we're working with something familiar. But we also want the relevant model output so we can look at the processes. And we also want to be able to play with the model configuration a little bit so we can test various hypotheses. And access fire has been really valuable over probably about the last 10 years or so in running case studies and producing simulations. So the basic structure, we've seen similar slides to this already today. Access fire is in the UN model. I'll talk a little bit about that in a minute, but basically the atmospheric model provides surface inputs to the fire spread model. The fire spread model calculates fire spread and then passes latent heat and sensible heat fluxes back to the atmospheric model, and each time step the whole cycle goes around. It's useful to take a little bit of a step back and look at what we do in Australia in terms of the modelling framework and what we'd kind of call the access family. So in Australia, we use the Australian Community Climate and Earth System Simulator, that's ACCESS, and we use that for both weather and climate modelling. ACCESS is the Australian version of the UK Met Office's unified model, so we're part of the Momentum partnership that the UK Met Office have, and we've been developing and testing the access model in Australia by the Bureau and also other institutions. So CSIRO and a number of the universities are involved in developing the access model and running it for both research and operational purposes. In the unified model, you've got a whole range of different components. For our purposes for access fire, we're really looking at the atmospheric and the land surface schemes. And importantly, and this is probably a bit of a distinction between some of the other models that we've heard about today, the fire source code sits inside the land surface scheme component, which is the Joint UK Land Environment Simulator, or JULES. So the fire component sits inside the land surface scheme and it interacts with the atmospheric component of the model directly through the land surface scheme. So we've got this whole suite of different access configurations that we use. Access G is our global model for NWP. Access C is our city-scale model. We've got Access S, which is our seasonal model, which goes out to 3 months ahead. We've got in the pipeline, which is going to come operational in 2027, I think now, the Access A model, which is an Australian region model, which is our next generation convective scale model for the whole of Australia. At the moment, it's broken down into smaller parts around the cities. We've also got the Barra model, which is our reanalysis model, so that's going back 30 years in time. And we've also got BARPA, which we use for climate projections for our region, which is going forward in time. And then we've also got the nesting suites inside the Access model where we can nest down to higher resolution. So importantly, all of these different models that we're using for different timescales have got the same framework, so they're all familiar. So it's been a little bit of a different approach in Australia to some other places in that in some ways we've put all of our eggs into one basket with the Access model, but it also means that when we're comparing different models and different timescales, we're comparing like with like. So that's really important from the Access fire perspective because everything that we're running is familiar to people in operations and who are working in climate because it's the same model configuration. So most of our operational models we run on the Bureau supercomputer, and the research configurations, the research models, including Access Fire, run on the National Computing Infrastructure, NCI, which is in Canberra. So we've got a whole collection of models that we run operationally on the Bureau's computer, collection of models that we run in research mode on NCI. And yes, as I said, Access Fire, it's really valuable talking to practitioners because it's familiar from what they're used to looking at in real time. It's similar to the other couple of fire atmosphere models that we've heard about today. It's a little bit less configurable than WRF, so whereas in some of the models you can actually play with the settings and choose different parameterisation schemes, a lot of that is hardwired in the Access model. Harvey, who's done a lot of our model development, or pretty much all of our model development, has tweaked the turbulence settings to make sure that when we were putting big heat fluxes up through joules through the land surface scheme that we weren't crashing the model because we were getting major heat fluxes in. And apart from that, most of the settings in there are same as the main UM. It captures the fire modified winds. We spent a lot of time looking at fire modified winds, which are fascinating, plume dynamics, which are also fascinating. And in a number of cases, we've resolved the deep moist convection or the pyro-Q, pyro-CB, if you like, that we've seen in the observations. At the moment, we don't have any smoke or chemistry in there, and we don't have ember trajectories, but those smoke and embers are two things that we'd like to get in there. And importantly, one of the things that Harvey's done in the last couple of years is put in the fuel grids from AFDRS. So as I said, AFDRS is our National Australian Fire Danger Rating System. I'll talk a little bit more about that in a moment. But we've got in Access Fire now all of the fuel grids and all of the fuel models that are the same as AFDRS and also the same as Spark, which is our National Fire Simulator, which has been developed by CSIRO and by AFAC. So all of these things are comparing like for like, and they're sort of using and leveraging the same information. It's currently a research tool. It's computationally expensive to transition to operations, which is part of the reason we haven't done it yet. And it's been a really small research team. So most of the work has been part of me and part of Harvey for about the last 10 years now. So the investment has been pretty small, and particularly compared to some of the other teams that are working on coupled fire atmosphere models, ours is a very small team. All right, bit of technical stuff. For the fire ignition, we specify this in a config file. All of this is done manually at the moment. A lot of the time we'll put in a point location, the fire started here at this time, or often now what we're doing is getting from a line scan image from the agencies, working out where the fire line was, and then getting that line into the model as a starting point. From the atmospheric model, usually we use the Access G analysis fields. That's our starting conditions, so kind of similar to using the ERA or the ECMWF grids. We've got 140 vertical levels following sigma coordinates closer to the surface. Usually we run 300 metre horizontal resolution, but sometimes when we're looking for something interesting, we'll crank up the computational cost and go to 100 metres. And Access Fire is coupled on the innermost nest. So the nests run sequentially, and only the inner nest knows that there's a fire in it. The outer nests have already finished by the time the fire kicks off. As I said, the latent and sensible heat fluxes go up into the atmospheric model through joules, the land surface scheme. We've got the AFDRS fuel grids and fire spread models. There's also options in there for rothermal, the CSIRO, forest and grass, and also MacArthur. We're now really just using the AFDRS, but in theory you can put in any fire spread model that you want or any fuel model that you want. And we don't have any disruptions in there, so it doesn't know about roads and rivers and things like that. But for most of the fires, well, for all of the fires that we've been looking at, we're looking at large enough fires with enough fire and atmosphere interaction that it's just, the fires are just jumping any minor disruptions anyway, so it hasn't been an issue that we don't have those disruptions in there. When you look at the model output, it puts fire-specific data and atmospheric-specific data into two separate output files. Usually we get 10-minute data for the atmospheric fields. We can get 1-minute data if we want. It costs more. And usually we look at, for the two-dimensional fire data, we get 1-minute surface fields, and that includes the 10-metre winds and the fire parameters. We can only look at case studies. Unlike some models, you can't run idealised simulations, so we can only initialise it from a past event that actually happened. And we're really looking at landscape scale fires. Most of the fires that we've been looking at have been 5,000 hectares or greater. It's been run on 10 case studies so far. Can't be run in real time. Very high computational cost and storage, and you've got to run it on a supercomputer. So just as an example, this shows the Woolloomooloo nesting configuration. So first about here, this was a fire in 2021 that was just northeast of Perth. At the moment, we're running the UN version 13.0, so this is all consistent with the new Access A configuration that we'll be going to as an operational version in a couple of years' time. In theory, we can run the model for anywhere in the world. We've only run it for Australia, but as long as you've got the ancillary files, which should be there because Access G is a global model and the UM is a global model, and as long as you've got fuel data, you should be able to run it for anywhere you want. And all you need to do is put into the configuration file where your fire is, then where it starts, and off you go. All right, as I said, one of the big things that's been put in the last couple of years in terms of model development is putting in the AFDRS, the Australian Fire Danger Rating System, which was operational in 2002. And one of the big things about AFDRS, major effort, particularly by Belinda from RFS, was putting together a nationally consistent fuel grid, which we didn't have until then. So we now have a nationally consistent fuel grid around the country. There are 8 main fuel types, and I think it's 128 sub-fuel types. And those are all updated by the fire agencies for things like time since fire, vegetation type, and a whole range of different inputs. So for Australia, it's a little bit different to what some other countries do, what the US do, in that we've actually got individual empirical fuel models for each fuel type, or individual fire behaviour models for each fuel type. So for these 8 different fuel types, each has its own set of equations rather than the same set of equations applying to all fuel types. This means, of course, that we're consistent with operations. One of the big steps forward has been that since we put in AFDRS, we've actually seen really significant improvements in the verification against the actual fire perimeters. So it was sort of an unintended consequence of let's get the best fuel data in there, that all of a sudden our simulations improved. Great outcome. All right, that's the technical stuff. On to the simulations. So this was one from Kangaroo Island. This was one of the Black Summer fires in January the 3rd. This fire, one of the fires on Kangaroo Island, well, a number of the fires on Kangaroo Island took a major run. So just for info, the Kangaroo Island is about half the size of Corsica, and half of the island burned during the 1920 fires. So an area of a quarter the size of Corsica burned. The fire, the point that we're looking at is just underneath that Pyro Q there. It wasn't a Pyro CB, it was a Pyro Q. And what happened was the Cape de Coudie lighthouse, named after a French explorer, was one of the few spots on the island that didn't burn when the fire took a major run. And when we ran Access Fire, we got a really interesting output. You can see in through here, this was the satellite imagery from the 10th of January. See that tiny little green bit down there? That was the bit that didn't burn, which is where the lighthouse and the lighthouse cottages are. And when we ran Access Fire, we actually saw that the winds turned for several hours over that area. So the fire never burned down into that area as a head fire, it only burned through as a flank fire. And on this day, of course, the temperature of the island, across the island, was well up into the low 40s. I think it hit about 45 degrees at Pandana. but the sea surface temperature, because this is the Southern Ocean, is only about 15 degrees. So you got all of this turning of the air as it came off the hot land and over the cool ocean. So kind of remarkably, the simulations reproduce what happened in real time, which really gives us confidence that the model's doing the right thing. Another fire that we looked at in detail from Black Summer was the Green Valley fire. This was the day before a lot of the fires made major runs on New Year's Eve. And in Green Valley, there was a fire-generated vortex with tornado strength winds. So we did a lot of work. We've actually got a publication coming up on this event and another event. But fire whirls happen all the time on fires. When you start looking into it, it's actually a really common phenomenon. There's fire whirls all the time. The question is, when do you get a fire-generated tornadic vortex where you've got wind speeds up around 300 or 400 kilometres an hour? And what are the ingredients that produce a fire whirl of that magnitude? So what happened was, you can see in the video here, this was provided to us by RFS. You can see the towering convection column. We were talking earlier about the counter-rotating vortex pairs, and you can see that here in the image. This is obviously several hundred metres across, quite slow rotation, and out of this rotating convection column, it was a shedding or a wake vortex, much smaller, probably about 60 metres across, and that impacted a fully loaded fire truck. So there was a fire truck which was 12 tonnes in weight, and the vortex actually overturned the entire thing, and they could work out from where the tire marks were that the truck hadn't just landed on its side. The whole thing had been lifted up into the air. So a 12-tonne fire truck was lifted up by the vortex there. So RFS asked us to look into it. There was a young firefighter who was killed in the event, so there was a coronial investigation, and RFS asked us to look into the event in detail. So we ran simulations using Access Fire, and we were really looking for the ingredients for vortex formation, so looking for the spin and the stretch components in vortex formation. So stretch, of course, we're looking at the updraft. What we've got in this image here, these are the upward motion, so the vertical winds at 1.5 kilometres above the surface. You can see in here 2 pulses which are consistent with the counter-rotating vortex pairs. The red perimeter in through here is the fire line, and when we look at the cross-section through A and B, you can see these 2 really strong pulses up to around about 5 kilometres. So this is consistent with the kind of boundary layers that we see in Australia on hot days. We've often got boundary layers up to around about 5 kilometres elevation. We ran these simulations at 2-minute time intervals, and this pulse of up motion, you can see the little black dot in there? That was the location of the fire truck. So it's right on in terms of location, and also the timing matched pretty much spot on in terms of when the incident occurred. When we look for the spin component, looking for the low level vorticity around the red fire perimeter, we've got a huge amount of inflow, a lot of fire modified winds, lighter winds behind the head fire, quite strong winds, and you can see sort of there's loads of different sources of rotation in through here. So all of the ingredients for vortex formation were captured in the model. The model that we were running in this case, I think, was 300 metre resolution, so we're not necessarily going to get the 60 metre resolution of the actual vortex that occurred, but all of the ingredients are in there at the right time, at the right location. And this was in a valley, so you've got really quite light winds ahead of the fire line in the valley. So again, another example where the access fire is capturing the processes that we're looking for in trying to understand what's happening with the fire behaviour. This was a Corryong fire. This was another of the fires that ran on New Year's Eve. The fire spread at a remarkable 36 kilometres in the overnight period. So there's 6 kilometres an hour at times. There were a number of fires on this night that made overnight runs. The Corryong one was one of the most extreme. It was New Year's Eve, so the pink dot here is the town of Corryong that was impacted. There were a lot of evacuations in place and a lot of roads blocked, so huge amounts of impact to communities. So part of the question here was, why did the fire spread 36 kilometres in the overnight period? And this goes back to the presentation that Tristan did earlier. What we're looking at here is a cross-section along this black line through the red fire perimeter. We're looking from the surface up to 9 kilometres. The black is topography, and the pink and yellow is where the active fire is. The red is wind speed, and you can see that we've got a low-level jet in through here at less than 1,000 metre elevation with wind speeds up around 70 or 80 kilometres an hour. Now, you can see that you've actually got the fire front, or where the fire is, and the fire plume shooting up ahead of it is actually interacting with the winds above the surface. So we've got remarkable kind of fire plume interaction with that low-level jet. For these simulations, I think we were running 20 tonnes per hectare in terms of the fuel load, but we did find by experimenting with it that there was actually quite a lot of sensitivity between the fuel loads and the fire and atmosphere interactions, which is what you'd expect. And we were really looking at what were the fuel loads that were available during black summer, because they were much higher than what we would otherwise normally expect to see. Now, of course, we can run the fire atmosphere model with the coupling on and off. So when we run it with coupling off, you get what you'd expect to see, which is a near-surface inversion forming, and you've got separation between the elevated winds and the near-surface winds in the overnight period. But when you turn the coupling on, you can see a remarkable change in the structure of the winds above the surface and the fire plume, the wind's shooting up in the fire plume ahead of the fire, and behind it it's really pulling in these stronger winds down around the surface. And we've seen this at a number of fires now. Every time we go looking for it, it's in there. Our fire behaviour analysts are looking for this systematically to look at doing their fire predictions in the overnight period in terms of what are the overnight winds, what are the fuel loads at the surface, and is the fire plume likely to interact with the winds above the surface and bring those winds down. All right. So this is another of the fires that we've done. This was the Wirraloo fire. I showed it briefly earlier. This one was just northeast of Perth in 2021. And just wanted to show in here that obviously the fire coupling can make a significant difference to the fire spread. So yellow is our coupled simulations, and this is a run that it did in the overnight period. And the cyan is the uncoupled simulations, and you can see as well, we'll have a look at the animation in a little while, but you can see that there was a lot of fire spread on the northern flank of the fire in the uncoupled simulations compared to the coupled simulations, and we'll see the winds converging on that edge in a minute. Going back to Himawari data, satellite data, we were talking about this one yesterday. We did a comparison of the simulations and the Himawari RGB enhancement, and you can see in through here, the green is the simulated fire perimeter of the Wirraloo fire, and the hotspots are with the RGB enhancement. And we actually, over the first 12 hours of the fire, got a remarkable match between the simulations and the Himawari hotspots, which is reassuring. All right, this is a bit of a slower animation. So this is the Wirraloo simulations that we did with Access Fire. These are the 10-metre winds, but we're not looking at all of the winds, because if we looked at all the winds, it'd be too crowded. So I think this is every 10th wind vector plotted. The fire started just after midday. You can see the fire modified winds. So if you watch near the head fire, you see these pulses in the fire modified winds. And as I said, we're not plotting all of the wind vectors here. So when you look at it in more detail with more wind vectors, you see stronger fire modified winds. Going back to a comment that I think it was that Adam made earlier, it's really interesting in terms of what winds do you use for your domain. There's a huge amount of wind variability across the domain. There were two periods in this fire. So the Wirraloo fire in the first 24 hours had two significant runs. It had one run just after ignition, and then it had another run through the overnight period when we had a low-level jet form which accelerated the fire spread overnight. One of the things that we were curious about was why the fire took an initial run and DFES, who are the Western Australian Fire Agency, didn't put it out immediately. Because in some ways, it was kind of surprising that it got going, because DFES are remarkably good at putting fires out. And I've seen cases where there's worse conditions than this. There's an ignition, next thing you know, they go, yep, we've got that one, it's fine. So one of the questions was, why didn't DFES get onto this one immediately? Why did it take a run? And so we went in looking at the dynamics, trying to figure out what was going on, and the answer was we couldn't find anything. When I asked Jackson, one of the guys at DFES, he said, oh, well, that's because there was no suppression in the early stages. So when the fire ignited here, it was running into a whole collection of houses and properties. So all of the initial response from the fire agencies wasn't about putting the fire out, it was about doing evacuations and protecting houses. So the reason that it got going at the moment was because it got going at the beginning was because all of the firefighting activities were on protection rather than on suppression. So it just goes to show that you can't just look at the dynamics of what's happening. You've actually got to take a step back and look at what's happening in the broader environment and all the different ingredients that are happening in the landscape. All right, so it's 7 o'clock in the evening now. This is 1 minute data that we're looking at. And you can see the winds have dropped off. So we've got winds now around about 10 metres per second. 10 kilometres an hour. So much lighter winds in the early evening period. And then we'll see the winds pick up late evening and the fire will take another run. You can see here, I was talking before about how we've got a little bit of turning of the winds on that northern flank. So if you think back to the coupled and the uncoupled simulations that we saw, part of that is because you've got in what was a general east-southeasterly flow, you've got that kind of continuous turning towards the slightly northeasterly on the northern flank. So we can see going in now to 9 o'clock, you can see the winds are starting to pick up a little bit. Seeing the fire-modified winds starting to surge. And there's a scarp just along this line here. So this is a sort of flat scarp and it drops off onto the coastal plain just around through this area. See the southerlies in through here? This is a light sea breeze coming in the afternoon period and early evening period, and then it drops off. And then we start to see around about 11 o'clock in the evening, the winds start to pick up, the fire hits the scarp, and when the fire hits the scarp, we've got quite a lot of interaction with the low-level jet above the surface, and we've got accelerated fire spread. And you can see a lot of the activity still on that northern edge of the fire rather than the southern edge of the fire. And this is as the fire's running down the scarp. You can see the enhancement of the winds. So even though we've got stronger winds in the environment, we're still getting much, much stronger winds near the head fire from that coupling process and the winds above the surface mixing down. All right, so what we just looked at, well, as I said, was a filtered wind. What happens if we look at every single wind in the 100 metre grid? And this is at 1 metre resolution. So as you can see, huge amount of variation over a very small domain in terms of the wind speed and also the wind direction. But what we can also see here is some junction fire behaviour. So Alex was talking yesterday about junction fires, and you can see in through here, you've got what's effectively a junction fire, and then you can see the surge and it fills in. So there's a whole range of processes that we're capturing now in the coupled fire atmosphere model that we didn't actually intentionally set out to resolve, but they're coming out of the physical processes in the modelling framework. All right, so the Currowan fire. This was one of the fires that took a major run on New Year's Eve in 2019. The fire had been going for about 6 weeks by then. It ignited mid-November, so there was quite a large burned area by New Year's Eve. RFS were issuing, RFS, the Rural Fire Service in New South Wales, RFS were issuing these red maps, and you can see this was issued the day before, for the 31st, and they were expecting the major fire run to be on that northern edge. The fire was expected to stay west of the Princes Highway. So the Princes Highway is one of the biggest roads in Australia, 6-lane highway. And what RFS had done was put in over 100 kilometres of containment along the Princes Highway to try and keep it on the western side of the highway and not run towards the coast where there are a lot more communities and a lot more people living. The fire crossed the 6-lane highway and impacted the towns in through here of Conjola and Conjola Park near Lake Conjola. And there were 3 fatalities at this fire. And RFS did get quite a lot of criticism for it because they were expecting the fire activity to be other places. They didn't have a lot of trucks or firefighting appliances at Conjola. The Bureau was really overwhelmed in terms of the number of forecasts that we were being requested to do, so we'd put a cap on the number of forecasts. So the incident weather forecast for this fire was up here inland of Nowra, and And one of the criticisms or the questions was that neither the incident weather forecast or the automatic weather station observations matched what happened at the fire ground. So there was an automatic weather station here at Ulladulla, we'll have a look at it at the moment. There was another one at Jervis Bay, and there was another one at Nerriga further inland, and none of those matched what happened at the fire ground. All right, so RFS took a line scan at 9:50 in the morning of the Currawin fire. So you can see this is where the active fire was. The main active fire was in through here. We also had active fire in these two locations. This little bit here was the backburn that RFS had put in the overnight period. And we had a little spot fire here on a hill at Golden Flats. An hour and a bit later, there was a sentinel image that was taken, and you can see that this area had filled in between the main fire and the backburn. This fire further south hadn't actually made much of a run, but the spot fire at Golden Lane had really taken off. It had also spotted across the highway, so we've got the highway in through here, so we had spots across the highway by 11 o'clock in the morning. And you can see that it was probably that Golden Lane spot, that small spot fire that had escalated significantly. We've got a reasonably good chronology of events during the morning, but in the afternoon there's a lot more uncertainty about what happened because there was just so much happening across the whole country at that, or the southeast of the country at that point. This is the final, or the burned area. This was the next sentinel image that was cloud-free. This came in on the 10th of January, and you can see where the burned area was extending across west of the Princes Highway. You can also see in through here Lake Conjola, which is obviously a lake area, and the fire had burned down towards Lake Conjola and then spotted across and burned to the north as well. When we look at the meteorology, so following kind of a typical case study, looking at all the different ingredients and looking at the broader environment, we probably didn't have a classic setup for a bad fire weather day in Australia. Our classic days would be when we've got TCs to the north, TCs or intense low pressure systems to the north of Australia, and a really strong upper trough. We did have a very stationary high in the Tasman Sea. You've got what's known as a southerly bluster wind change coming off over New South Wales. The area that we're looking at in Conjola is just underneath where that little low is at 11 a.m. in the morning. So not a real typical pattern for a really bad day, but certainly that change is always a concern for New South Wales. When we look at the 950 hectopascal winds, you can see the wind structure just sitting off the coast there, and you can see that change in extending across most of the continent. Interestingly, when you look at the upper charts, as I mentioned, you didn't really have the really sharp upper trough that we'll often look for, but this was the day where there was a major pyro-CB outbreak. I think it's still the most pyro-CBs anywhere in the world in a single day, and you can see with the split in the upper jet, there was a huge amount of divergence over southern New South Wales, so that divergence supported the up motion. When we look at the aerological diagrams, these were taken from Nowra, just a little bit to the north. Very typical inverted V profile up to around about 600 hectopascals, really hot, dry air near the surface. This is the 6 a.m. one. Near the coast, we had quite a very, very shallow, moist maritime layer sitting in with light winds, relatively unstable when you look at it, so the pyro-CBs aren't really a surprise over southeastern Australia. And then just 4 hours later, you can see the really shallow inversion had mixed out, a little bit of mid-level cloud had come in, a lot of instability, and that really dry air which gave us dew points below zero. Also note that the balloon trajectory here from Nowra was eastwards over the ocean, so the winds aren't being sampled over the terrain where the winds were a lot stronger. You're sampling here over the ocean with slightly lighter wind speeds. One of the big discussion points for this day was the pyro-CB, and an important point that we're trying to make is that you don't need a pyro-CB to get dangerous fire behaviour. Obviously, if you've got a pyro-CB, you've had dangerous fire behaviour going on at the surface, interacting with the boundary layer for quite some time. So this is the lightning for the 31st of December. We had lightning to the north near Nowra and lightning to the south, but there was nothing over the Conjola area. And also interesting to note that less than 10% of those were cloud-to-ground strikes as opposed to cloud-to-cloud strikes. As I mentioned, one of the things that RFS said was that the automatic weather stations didn't capture the conditions on the fire ground. This is the Ulladulla Automatic Weather Station just to the south, the Nerriga Automatic Weather Station, which was further north and also a fair bit inland. So you can see at Ulladulla that maritime air mass coming in the overnight period, quite light winds overnight, a northeasterly flow coming in from the ocean. Around about 9 o'clock in the morning, the winds turn around to the northwest and you start to sample that hot, much hotter, much drier air from inland. And then the wind change coming through just after midday, an incredibly sharp wind change, so a complete change in air mass over the space of a couple of minutes on the coast at Nerriga. Note here that you had lighter winds ahead of the change and stronger winds after the change near the coast, but in contrast, further inland, you had stronger winds ahead of the change and lighter winds behind the change. So at Nerriga, further inland, you still had that dry air and warmer air in the overnight period. It obviously had some kind of drainage flow with that consistent wind direction, but the northwesterlies from first thing in the morning around about sunrise, peaking before the change, and then lighter winds. And you've also got a time lag of about 3 hours, so quite a long time lag between when the wind change went through at the coast and when it went through further inland. And a sharper wind change as well, so a much sharper change in wind direction further inland. But obviously neither of those were really representative of what happened to the fire ground. All right, so we heard a bit from Adrian about radar data yesterday. This is the Captain's Flat or the Canberra radar, and what we've got here is the 100-kilometre range ring, so we're quite away from the radar. But you can see that really intense escalation after about 9 o'clock in the morning. So if we look at the 9:18 radar scan, you can see there's just a little bit of reflectivity showing up there. It's just picking up the hints of a plume. Less than half an hour later, you've got a really significant escalation in the plume activity. I find, the alert status was upgraded to emergency warning at 9:45 a.m, so after this radar scan. But you can see at this point, this is 9:42 at the moment in the morning, and you know that the wind change isn't due for another couple of hours, so there's nothing to prevent that fire from running all the way to the coast. I find this one kind of interesting because in terms of how do we interpret it, because you can see a fair bit in the early stages, but becomes very, very noisy. So in terms of making operational decisions from the radar data, it really does highlight that we need tools to be able to interpret what's going on, and probably automated tools as well, because it can get quite noisy. If we look more broadly about what's happening over southern New South Wales or southeastern New South Wales on that day, maintaining situational awareness with that number of fires burning in the landscape was pretty much impossible. It was incredibly challenging. So some of the fires have been burning through the overnight period. Not all of them had been active. This is our fire here at Conjola. You can see it popping up in the early morning period, and you can see that it quickly becomes one of the most active fires in the area. So how do you, from an operational forecasting perspective and from an SBAM perspective, maintain situational awareness across all of these fires? We've talked a little bit about vortices and fire generator rotation. You can see in the Doppler radar, you can see just hints of rotation and much stronger winds in this area around about the time of the wind change. So there's definitely the opportunity to get more out of that data. When we look at the satellite imagery, this is our Himawari water vapour, and this is the same enhancement that we look at in operations. We didn't have some of the hallmarks of a really bad day, so we're often looking for these really dry slots sitting above the fire environment. Obviously, there was quite a lot of moisture over southeastern New South Wales in the elevated layer, so not near the surface. Obviously, we had dry air, but it didn't have the sort of typical really significant dry slot day that we'll often look for on a bad day in Australia. When we look at the fire temperature RGB enhancement, this little red cross here is our fire. I didn't think that one was going to play. This is our Conjola, and you can see the escalation in through this area. It's also a really good example of how satellite data can be incredibly useful when you've got it, and then as soon as you've got elevated cloud cover, it becomes useless very, very quickly. We have had quite a lot of conversations from looking at a number of different fire events about whether or not we can get more detail out of the warm fire, very warm fire and hot fire that we have at the moment operationally, and there's got to be a little bit more quantitative measures that we can take from the satellite data. All right, this is the same enhancement zoomed in a little bit over Conjola. The red cross again is showing us Conjola. This is 9 o'clock in the morning and 12:40. So you've got that remarkable escalation in spatial extent and also in intensity from the hotspots through that time period. There's a couple of things that I think are really worth thinking about here, and this goes back to Ronan's presentation from yesterday. A lot of the time with the satellite imagery, we're asking the question, is there a fire there or is there not a fire there? We're not asking the question, how is the fire changing? So I think that there's a lot more information that we can get out of escalation. Is the fire escalating? Is the fire de-escalating? And how is the fire moving from the satellite imagery? Noting, of course, that it's 2 kilometre resolution is what we've got available at the moment, but we're also seeing massive advances really quickly in the temporal and the spatial resolution of satellite data and the number of platforms that are up there. And we're not really planning for the future in terms of how we're going to be using this data down the track. And I think as well, there's probably some opportunities for machine learning in looking at a number of these fires as well. So it's not something that we've had scope to do inside the project, but it's certainly something that we thought about. All right, onto the access fire simulations. So Harvey did a collection of simulations from this. He took from the line scan image that we had at 9:50 in the morning, where is the fire area, and used that as the initial fire line to run the simulations for. What we've got in through here is the simulations that we've run. The orange one is without spotting and the white one is with spotting. I said before, we don't have spotting in the model. So what we did was we spoke to our friends, colleagues at RFS and said, could they run Spark on the event? They ran Spark, got spots out of Spark, and then we reran Access Fire with the spots out of the Spark model. So it's partly about trying to get the best out of the different frameworks that we have. Noting that Spark runs on a laptop really quickly and it's got a lot of functionality in terms of changing things. So we're trying to show, well, firstly, we're trying to get the embers because we knew that they were important, but we're also trying to show that you can actually use these modelling frameworks in a complementary way. For information, these are the fuel grids that we had from AFDRS. Obviously, mostly sort of forests back through here and in the coastal environment. Wet forests and dry forests tend to behave the same when you've got drought factors at 10. So when we have these really, really dry conditions through New South Wales in black summer, the wet forests and the dry forests were effectively behaving the same, and quite a lot of crop and pasture. And the purple area in through here is the lake, which is classified non-combustible, so you can see that the fire stopped moving there. All right, so these were the Spark simulations that Jeff at RFS worked through us with. So he did a number of simulations, and one of the things that he said over and over again was that he simply could not reproduce the observed fire spread using the surface winds. So he had winds from our operational forecasting system, and he had winds from all of the automatic weather stations, and he simply couldn't reproduce the observed fire spread, even including spots with the winds that he had. So you needed to have the coupling and the interaction, the winds above the surface, supporting the fire spread in order to reproduce what actually happened. This is the first one that he did with standard settings for Spark, and we were talking earlier about what the probability is of a new ignition. So one of the things that we're kind of having conversations about is what's his probability of extinguishment. So when you've actually got a spot that lands, what's the chances that it's going to start a new fire, and what's the chances that it's going to self-extinguish? Now this number apparently came from work that Derek did about 10 years ago that he put into Phoenix, and the scaling factor, which as you can see is a interesting little decimal point number in there, has got a lot of sensitivity about it. And we do know from Black Summer that the chances of any, or the likelihood of any ember starting a new fire was higher than normal because the fuel beds were so dry. So it doesn't actually make sense in a way to use a constant probability of ignition for a new spot, because you do have that variation in fuel beds. And of course, we know it's entirely plausible that there were more long distance spots than we got produced in the simulations. All right, so this was the next simulation that Jeff did using Spark, and he produced this spot. So we reran Access Fire with this ember in it. And you can note in through here that the trajectory of the elevated wind from the spot was more northerly than the surface spread. So you've got sort of inferred surface spread there in a west-northwesterly, and the spot direction was a north-northwesterly, which is what you'd expect from the winds turning with height. So these are the isochrones from Access Fire, noting this is around about 18 kilometres in through here. We've got hourly isochrones on this side, the half-hourly isochrones on this side, which I think are more interesting because you get more detail leading into the wind change. A few things to note. So Harvey obviously set up a number of different fire ignitions in his 9:50 start, and you can see that they ran at different times. So just looking at the orange contours, you can see that each fire didn't run at the same speed. They all ran at varying speeds for the first couple of hours. You can also see as well, one of the things that's really interesting, after the wind change went through at 1 o'clock, this fire to the south took a remarkable run to the north. So this is around about 5 kilometres in half an hour in through here. And we know that at least one of the fatalities from the coronial reports was in through this area at yada yada. And there was a very well-known Australian paper that was written by Phil Cheney, Jim Gould and Lockie McCaw back in 2001 that named this zone in through here the dead man zone, and it's the area that you don't want to be in when a wind change goes through because there's basically no opportunity for egress, and that was certainly the case for this fire. So one of the questions that we went looking at was, well, why were there fires running at different rates in the northwesterly, and also what was happening in through here behind the wind change. All right, so these are simulations. We've done a couple of different runs of these. You can see the spot in through here that we added, which starts off a bit slow and then accelerates. You can see this one in through the southern fire is running a lot faster than this northern fire in the morning period. We've also got some coalescence in through here, so you note the couple of times where the fires join, and we've got some interesting processes happening in the fire modified winds and the coalescence. Really strong winds around this head fire through here. This one's still running a little bit slower, but it takes off in a little while. You can see our spots slowed down a bit, but it's going to accelerate. A lot of activity on the northern flank in through here. These two fires will join in just a minute. And then we'll also start to see the southerly wind change come in. So here's our southerly wind change coming up. And just watch the fire activity in through here as the wind change goes through. And also note the variation again in the wind speed and direction across the 20 by 20 kilometre domain that we've got. So if you were going to be doing a forecast for this event or for this location, choose a wind speed and choose a wind direction that accurately captures what's going on. We've got time to run it again?
I don't know how long you
I've only got a couple more slides.
Yeah. You have 10 minutes of,
Okay.
with questions, so depending on how many questions you have.
Do you want to see it again? Yeah. All right. Oh, I've got a drink. We can look at it again later as well. But it's really remarkable. And look at, in through here, you've got light winds, onshore flow in through the coast. Hugely varied winds around each of the individual fires. Just noting the wind speeds in through here ranging up around 50 to 60 kilometres an hour. And then when you've got the pulses in the fire modified winds, you're up around 80 to 100 kilometres an hour. And at the same time, you've got 10 kilometres an hour showing up in the domains. And really interesting to see some of these variations in spread, speed and direction across a relatively small domain. And then the strength of the change and the variation in the change as it goes through the domain. And this incredible fire run through yada yada. And we don't really have the information to verify that, but it's certainly consistent with the ground report. So there was quite a lot of media coverage of the event. And there were a couple of news articles, and there was also a book written, and that surge is consistent with what people were observing. All right, so what was going on in the processes? Yeah, doesn't want to work. Okay, so what we're looking at here is a cross-section from north to south through the fires. What we've got in through here, this is the wind change. So this is south and this is north. 2 different time periods, 10 minutes apart, so very quick transition. You can see the very shallow, so less than 500 metres deep, southerly wind change coming in through the coast, coming in off the coast, and quite a strong surge at the beginning of it. What we're looking at here is the winds that way, or the winds that way are southerlies, that way are northerlies. The winds are coming out of the page towards us are the northwesterlies. So most of the winds in through here are the northwesterlies. You can see as well the depth of the boundary layer and the stronger winds obviously behind the change. But just seeing through here how this really shallow layer transitions in a 10-minute period, and you've got some of the strongest winds sitting in through here on that change line. And we think what's going on here is that you've got the 2 fires, and the fires initially have got separate plumes. And as the change is coming in, the 2 plumes are trying to merge because the plumes are going to preferentially have a single plume rather than 2 separate plumes. And that process is actually accelerating those wind change, those southerly winds through yada yada. So we're still working on this and we've got to investigate it a little bit more, but we think that that's what's going on. So remarkable processes and obviously really fast fire spread that you're not necessarily going to resolve through any other modelling approach. So this is a cross-section. This is one that Kevin did. So this is looking at the northwesterly flow. So this is the head of the wind change, or just as the wind change coming in. And this is just looking at what the processes are that the model's actually resolving. So this is a cross-section along the green line through here, through the southern fire that we had. You can see that the red is up motion in through the plume. You can see, as we'd expect, that the strongest up motion is actually halfway up, partway up the boundary layer rather than at the surface. Note the tilt in the plume. As I said, there wasn't any pyro CB at this fire. There was pyro Q, we saw that on the satellite image, but obviously a huge tilt downwind. So there's a lot of discussion around plume collapses and pyro CBs and impacts on fire grounds. But you can see here that a lot of the time with that plume tilt in a strong northwesterly, anything that's happening above the boundary layer can be 10 kilometres or more downwind, which reduces your chances of seeing any kind of fire ground impacts, which is a different scenario to what we looked at earlier when we had that rotating convection column over the Green Valley fire where everything's vertically stacked above the fire ground. So we've been talking to some of the fire behaviour analysts about the whole idea of sort of everything being vertically stacked compared to being tilted and the different processes in there. So green in through here is cloud liquid water, yellow is cloud ice water, the little stippled area is precipitation, so we're capturing the precipitation. You can see the perturbations in the potential temperature as that plume's punching up through the boundary layer, and you can see in through here the potential temperature lines are showing the wind change coming in and cutting off the plume. So the model's resolving a whole collection of different processes that we know are important, but we often can't take measurements in a fire environment, so it's really valuable to be able to get these things in a modelling framework. All right, so Access Fire resolves the fire and atmosphere interaction processes. We've learned a lot from running simulations of case studies. The processes over and over again are consistent with talking to people who are working on the fire grounds. So we'll go out and we'll present some of the work to firefighters and they'll say, yes, that matches what I saw on the ground. We've had a really significant improvement in performance by putting in the AFDRS grids and particularly the 8 fuel models. We've put a lot of effort in the last couple of years to get the framework easier for new users to use. So there's the possibility for student projects, which we probably wouldn't have had a few years ago. And we've talked to a couple of people about rerunning the Canberra fires back in 2003. It's set up for Australia, but in theory we can run it somewhere else as long as you've got the ANSIL files and the fuel data. Most of the work has been part of me and part of Harvey, so it's actually been a really small project. And as I mentioned to a couple of people, we've been really slow to publish results, and we know that we need to catch up on that and make the findings more available to a broader audience. We have spent a lot of time talking to fire agencies. And as I mentioned as well to a couple of people, a lot of the funding that we've had has been to do case studies with the fire agencies rather than model development and testing. So that's really why we've been doing case studies rather than more systematic approach to the research with the model. In future, we want to do more case studies. We'd like to get the code back on the trunk. At the moment, it's on a branch, which means that our team can use it. If we get it back onto the trunk, it means that it's available for other users. And we want to look at more processes, including EMBA transport and smoke and chem transport, and also to try and get it running faster closer to real time and closer to operations. But one of the things that I guess is sort of in the bigger picture is how do you integrate all the information that we've talked about today, including things like spark and access fire and the radar data and the satellite data and all of that information into real time, particularly when we can have major events that are running really fast. Thank you.
Thank you. Thank you.
Thanks.
And, so with the next question, we have a time for a few questions. Any?
Sorry, I'm here all week.
Yeah.
No questions?
Okay, a question. Yeah, thanks for the presentation. I've seen that in many of the fire you have some inhomogeneity into your heat flux in the back of in the cooling area. So it's like the color bar that was red to yellow. You have a bit of yellow that stay in the background.
Yeah, yeah, because there's going to be different areas on the fire perimeter that are burning. So the active fire isn't all going to be at the head fire. You're going to get active fire at other parts.
But some of them were staying like quite far after the fire front passed through, and then you had some like hot spots at the back.
It's probably partly an artefact of the plotting as well. So we had been focusing on the head fire and where the main head fire was. So you're talking about the yellow and pink lines on the black topography.
It was, I think, on the Wallow or the fires. You had at the back some yellow spot, but I have a very bad view, so maybe those one, for example, the
in
one
there, yeah, that's where you've got fuel discontinuities.
But then they are emitting, or so do you still have hot spot at the back of the fire front?
In through here.
Yeah, those one there.
Yeah.
So they okay.
Yeah.
And do you see any pattern into the plume? No, they don't behave. They don't emit enough to make something. Okay.
No. Yep. I had a question about the Kangaroo Island simulation.
Yep.
I was wondering if the tornado that you see, you will also see it without the topography?
Good question. Possibly not, because so that was the Green Valley one. In through here? Yeah. Possibly not, because part of what we looked at when you look at cross sections through the fire is that you've actually got, I've got another simulation I can show you later when we sit down in front of it. There's actually quite a lot of separation in the flow over the topography. So the main winds, the background winds were actually a lot stronger earlier in the day, and then they dropped off late in the afternoon period. And when you look at the flow over the topography, it really separates, and then you've got really quite light winds in the lee of the slope. So that's consistent with a lot of work that Countryman did, and also other people. It's also consistent with the Bear Fire or the Car Fire, one of the ones that Neil looked at, where you've also got that fire-generated tornadic vortex on the lee slope or at the bottom of the lee slope, and that's probably at least partly because you've got that separation of the flow, the stronger winds going up and then lighter winds at the surface, which means that you've actually got the ability for the vertical up motion without it to develop without it shearing off. So we think that that combination of factors means that you don't get the shear in the same way that any kind of shear is going to cut off that vertical circulation. So yeah, certainly the lee slopes are an important factor there.
So Thank you for your presentation. I have a question. So you're saying that you exchange a lot with the fire operational, and I was interesting about your experience concerning what is their expectation about coupled wildfire atmosphere model and what were the needs that they communicate with you about this new type of modeling and the type of results that you can communicate them.
Yeah. Well, in Australia, there's really an awareness that some of the surface-based models or the empirical models were taken or made under a relatively constrained set of situations. And it's really the high-end fires, the extreme fires, where the models simply aren't behaving. And there's I guess a real awareness now with the fire agencies that a lot of the processes that we see at those high-end fires are because of the fire and atmosphere interactions. But at the moment, we simply can't run the model in real time because of the computational expense and also the amount of time that it takes to set it up. So the fire agencies are keen for it. Nobody's got the investment to make it happen. But what we are trying to do is, and we've got a project in the pipeline at the moment, to try and run access fire and develop parameterisations or rules of thumb or parameterisations from the simulations that then we can use inside Spark as an enhancement to Spark, which can be run more quickly in real time. So there's probably a couple of different approaches that we're taking. One is to train the fire behaviour analysts and the fire meteorologists in these processes so that they can identify them through pattern recognition. But we also really, particularly from a coronial and investigation point of view, we need to have a systematic way of doing it rather than an individual way of doing it. So that's why we're working towards developing parameterisations that can then go inside Spark. But it's as I said, it's a small team of people, so there's a limit to how much we can do at the moment.
Okay, thank you.
One more.
I think Laure had a question.
Madame.
Thank you. That was a really nice presentation. Joules. The development of Joules is by the Centre of Ecology and Hydrology in Wallingford. Do you work with them? Because they also do work they have fire sort of projects as well. My second question is on soil moisture, and there is a really interesting soil moisture measurement technique now with it's called CNRS, the cosmic ray, and Australia has a project within CSIRO, Cosmos, and I think there's like 15 stations, as well as the Centre of Ecology and Hydrology in Wallingford run a really dense network of 50 CNRS stations, and they actually use Joules to kind of get sensible soil moisture out of this. So there's like these two aspects. One is the fire research and the Joules development within the UK, as well as the CNRS.
Yeah. I've spoken a bit to the people in the UK, so a lot of their interest is really on the fire emissions at the top of the atmosphere and how that's affecting climate processes rather than the fire behaviour questions. So those are sort of the conversations that we've had with them. In terms of Joules, we have spoken to the people who work with Joules a little bit about getting the fire model in there, but their interest is really in the hydrological aspects of it rather than the fire model aspects of it. In terms of getting the soil moisture and the fuel moisture right, that's a massive challenge, and we really need a bigger project to do that. And we've talked a lot about in Australia recently about we need to move away from the systems that we're using at the moment to predict fire behaviour and look at what are the weather inputs, what are the fuel inputs, and then what's happening in the hydrological cycle over varying timescales in order to look at the fuel availability. Because the massive question really, particularly when you look at the coupling processes, is the fuel availability. And we found that by adjusting the fuel availability, whether it's 20 tonnes per hectare or 30 tonnes per hectare, you get a different outcome, and we really don't know what's happening. And we also don't know what's happening in terms of the dead vegetation and the live vegetation and what's burning, because now what we're seeing is that the MacArthur system, for example, was based on the twigs and stuff that's about the size of your finger rather than the bigger logs. And I've spoken to Mark Finney and to Lockie about how do we actually capture what the energy release is when you start to see some of those heavier logs in the landscape burning, and you just can't run experiments on it. So nobody really knows what's happening in terms of the energy release when we've got these big fires in terms of the fuel availability, but we do know that the hydrological cycles are critically important, and we know that those cycles are changing and we don't have a handle on it. But that's another project that, needs funding.
Thanks a lot. I think it's time to pass to the next one. Bravo.